Now that we've been introduced to the fundamental theorem of calculus part 2, what I'd like to do is run through a couple of examples together. So first example that we have is going to be the definite integral from 0 to 4 of the quantity 4 minus t times the square root of t dt. Now one quick note that I'd like to start with, anytime it starts with an integral sign, it's got to end with a differential. Could be dt, could be dx, could be dy, could be d theta. As long as this variable matches all of the other variables that you see in here, we're going to be okay. Now in its current form, we're not going to be able to work with it because we have two things that are being multiplied together. But we're going to do the same thing that we've been doing with square roots ever since the beginning of Calc 1, which is express it in terms of a power so that we can apply the power property. Now multiplying the t to the 1/2 power through the parentheses, we will have 4t to the 1/2 power minus t to the 3/2 power. Simply add those exponents together. Once it's expressed in the form of simply powers of t, we can apply the power rule for antiderivatives. Keep in mind that the fundamental theorem of calculus part 2 says find an antiderivative and then plug in the bounds. So with that in mind, for our 4t to the 1/2 power, the power goes up by 1 and we divide by the new power. But because it's already a fraction, we're going to say multiply by the reciprocal of that power. Minus, then for t to the 3/2 power, we'll do the same thing. Power goes up by 1. 3/2 plus 1 is 5/2. And then divide by the new power. Then we'll plug in our limits of integration. Limits of integration go from 0 to 4. We're going to start by plugging in 4. I'm also going to take the 4 times 2/3 and multiply those together. That'll be 8/3 times 4 raised to the 3/2 power minus 2/5 times 4 raised to the 5/2 power minus what we get when we plug in our lower bound of t equals 0. So once again, 8/3 times 0 to the 3/2 power minus 2/5 times 0 to the 5/2 power. Now, I have a technical term for what we see in the right part right here. I like to refer to this as a lot of 0. Very frequently, if you plug in a lower bound of t equals 0, x equals 0, y equals 0, whatever variable is equal to 0, frequently you'll get that everything cancels out. As far as the rest of this is concerned, we'll still have a coefficient of 8/3. 4 raised to the 3/2 power would be take the square root of 4, which is 2, and cube the result. That'll be 8. Minus 2/5 times, for 4 to the 5/2 power, that'll be square root of 4, and then raised to the 5th power, which will be 32. So ultimately we're looking at 64/3 minus 64/5. Get a common denominator for those and then subtract. We will get a final answer of 128/15. Good stuff there. So this represents the total amount of area that's under the curve y equals quantity 4 minus t times the square root of t in between t equals 0 and t equals 4. For another example, we're going to try out the definite integral from pi over 4 to pi over 3 of the cosecant squared of theta d theta. Now for this antiderivative, this is close enough to one of our basic forms, and I'm going to do a quick reminder. If I were to differentiate with respect to theta, the cotangent of theta, I would get the negative cosecant squared of theta. Now with that in mind, we don't have the extra negative sign in here, which is why when we perform our antiderivative, we're going to get an extra negative sign. And once again, this is going from pi over 4 up to pi over 3. So this will be a negative cotangent of pi over 3 minus the cotangent of pi over 4. Now cotangent of pi over 3, this is 1 over the square root of 3, and the cotangent of pi over 4 is 1. If I distribute the minus sign through, that'll become a positive 1 and a negative 1 over the square root of 3. I would be content with this as a final answer, and I know that WebAssign would accept that as well. But if you wanted to get really fancy with this, like say, get a common denominator and then rationalize the denominator, this could also be expressed as 3 minus the square root of 3 all over 3. We'll take a look at a couple more examples. This time the variable that we're going to be using will be y. So for this example, we have the definite integral from 1 to 3 of y cubed minus 2y squared minus y all over y squared. Now we'll do with this the same as what we did for the first example, which is do a little bit of algebra before we try to do a little bit of calculus. By that I mean I'm going to distribute this y squared through to all three terms in the numerator. That'll be y cubed over y squared minus 2y squared over y squared minus y over y squared dy. Using algebra to simplify all of these, we'll get the definite integral from 1 to 3 of y cubed over y squared, which is y, minus 2y squared over y squared, which will be minus 2, and then minus y over y squared, that'll be minus 1 over y. In this form, all three terms are ready to be integrated with respect to y. Applying the power rule to y, we will get 1/2 y squared. Applying the power rule to this minus 2, we'll get minus 2y. And applying the reciprocal rule, this will be minus the natural log of the absolute value of y. Oh my gosh, guys, my cat just took a crap and it smells so bad. Fantastic. So, plugging in our limits of integration, this is going to be 1/2 times 3 squared minus 2 times 3 minus the natural log of the absolute value of 3 minus, plugging in our lower bound of 1, this will be 1/2 times 1 squared minus 2 times 1 minus the natural log of the absolute value of 1. So good news is the natural log of 1, that'll just be equal to 0. Simplifying the rest of this will be 9/2 minus 6 minus the natural log of, well, absolute value of 3 is just 3. Distributing the negative sign, this will be minus 1/2 plus 2, and then minus the natural log of 1 is minus 0. Combining our like terms, we have 9/2 minus 1/2, that'll be 8/2, which is 4. Minus 6 plus 2, that'll be minus 4. And we'll have minus the natural log of 3. So final answer for this one would be the negative natural log of 3. And again, this represents the total amount of signed area, so it doesn't bother me that we wound up with a negative answer here. And one more example for these fundamental theorem of calculus part 2 problems. We have the definite integral from 1/2 to 1 over the square root of 2 of 4 over the square root of 1 minus x squared dx. Now for this one, I will ask you to recall with me the derivative with respect to x of the arcsine function. That is going to be 1 over the square root of 1 minus x squared. You'll notice that we have that almost exactly, but we do have that extra coefficient of 4. The way that that manifests itself for an antiderivative is that the antiderivative will have a coefficient of 4 due to the fact that it is a constant multiple. And as far as plugging in our limits of integration are concerned, this will be 4 times the arcsine of 1 over the square root of 2 minus the arcsine of 1/2. Simplifying each of those, arcsine of 1 over the square root of 2 is going to be pi over 4. That's the angle whose sine is equal to 1 over the square root of 2. Minus the arcsine of 1/2, that would be pi over 3. No, excuse me, pi over 6. Because again, that is the angle whose sine is equal to 1/2. Pi over 4 minus pi over 6, if we get a common denominator for those, is going to be pi over 12. And 4 times pi over 12 gives us a final answer of pi over 3 for that signed area. Good stuff.